So now we can revisit the derivative in this matrix notation, and we realize that derivative is a linear operator. When they teach you derivatives, they're all just defined in a limit, so they're all defined at the point x, you take. So you don't think of them as operation, they're just, if you had x squared, now you have 2 times x, but that's just some rule which is obvious. But the main thing that this operator we just introduced, this shift, which seems just coordinate change, nothing special, can be used to define what we mean by the different. And this comes under as many names as people who invent this, because everybody invents this sooner or later, because everybody has to discretize their calculations. So sometimes it's called stepping operator. This is when you think that you have somebody walking from site to site on a lattice, they're stepping. Or it's called shift operator when you think I'm just shifting the labels in a cyclic way on the lattice. And there are many other names for the same thing. And we wrote it originally as sigma in direction mu is a matrix with these 2 indices. But very crucially, we realized when you define it, you must define boundary condition, which for us will always be periodic. There are some lattices in physics where you have edges. You have a crystal which is 7 spacing along when you're working with graphene or something, a strip, and you do care about edge. But in a typical setting, the 2 settings, you either describe matter that's crystalline on angstroms but smooth in meters, then you think of it as infinite extent, or you're doing mathematical operation of approximate a continuum by discretizations, and then you take steps infinitesimal eventually. So almost always you want to think of it as something that's very large, and almost always you want to think of it in terms of periodic boundary conditions here, because you don't want to get in a situation where you get to the edge and rules of the game suddenly change and you drop off the edge. No thanks. So what you typically do if all directions are equally important, you take your infinite space. For example, you do that in quantum mechanics all the time to explain quantum mechanics to yourself and then to undergraduates. If you're in a finite d-dimensional hypercube, meaning you take your space, continuum space you started in, and you cut out a cube in that space, which is some distance in the 3 dimensions. And now, this is maybe dimension 1. This is direction 2. Originally, you had your axis there. This is direction 3. But you have finite patience, or your computer has finite patience, so you have to put some number of points, and we call that number L. This is an integer, which is the number of points in direction 1. You have to do the same in direction. Sorry, this is direction 2, direction 1, direction 3. And that means that we have subdivided this world in very small hypercubes, unit size in this integer representation. and they all have their corners, so this hypercube is filled out with points. So what used to be a continuum, X, is now discretized. So the vector, d-dimensional vector, is actually an L integer vector times the lattice spacing, where this L, sorry, L, like Lithuania, has entries in it, which are integer, but there's a finite number between 0 and L minus 1. So mathematical notation is we divide it by L, meaning something that used to be an infinite lattice is now just L integers. And we do this in every dimension. And that means that we have replaced a continuum in d dimensions by L to the points. And now this operation is comparing neighbors in various dimensions. And we'll need it to construct derivatives and construct our natural law, which often defined in terms of functionist derivatives. But hypercubic lattice has one wonderful feature that not only are these operators linear, but it actually doesn't matter whether I first shift in mu direction and then in nu direction, or I do it in the other order. In other words, these operations commute. So I showed you that you can think of this as a matrix in one dimension. But now, in general, this is now tensor because every point has a set of indices and you're acting on it to do something. But this makes it very easy because it doesn't matter in which direction you do them. So it's a bunch of one-dimensional products put together. So that's a very nice property of discretization on hypercube. And now we can rethink our derivation. Derivative is written as take a point and compare it to a neighboring point divided by a, take a limit, and you get Lth component because these are L dimensional vectors, so you can compute everything. But now we can turn this into operations of kind that we are real masters in this course. And that is, we can think of derivatives as operators. Now, operators, that's fancy stuff. But in this course, whenever I say operator, you just say, oh, he means matrix. And almost always this will work. Now, matrices, you know how to do. So let's see how that works. So I take a field, I want derivative in direction mu equals 1, 2, 3 to d, and I want to find the component of that field. And that is, I take the field and I multiply by matrix, where the first part of the matrix is the shift operator, and all it does, it produces a field at a neighboring site in direction mu, and I compare this with identity matrix, and I divide it by the distance along that direction, that's A. So I get my usual definition of derivative. Two neighboring points on a lattice divided by the distance. But I can just take this part and write it as an operator. And in one dimension, so I drop the index. The operator it has a constant in front, which is the lattice spacing, which might go to zero, might not go to zero, depending on the problem. But what's inside is, wonderfully simple. I have minus identity. That means on diagonal, I have minus ones, like turtles, all the way down. Compared to this matrix has zeros on diagonal, has ones above the diagonal. And because it's periodic, it has one here, and it has zeros every place else. Zeros, zeros. So the operator is an L by L matrix. There's no mystery about derivative anymore on a lattice. I can define any order derivative. So higher, forward derivatives. Now, when you think about it, there's something ugly about this definition because he arbitrarily chose to compare with point in positive direction. We could have compared with point in negative directions. So that becomes more dramatic when I take higher derivatives, and you'll notice they're not centered. They kind of compare stuff in the same direction. Doesn't mean much right now, but you'll see pretty soon why. So square derivative applied twice. Well, it's not a big deal because I take this and I square it. So, and let me set a equals 1. You can reinstate it, but it's just here a little bit tedious. I'll use lattice constants as a natural unit. So when I square this, I get the first matrix squared, then get a product between the two. And then I square 1. I know what that is. So that's just the second derivative. I can take kth derivative. And I use a famous theorem. I have something that has two elements. I raise it to power k. I use binomial theorem. There is a minus, so depending on how many powers of minus I have, that's for this guy. And then it's binomial theorem, so I have to take k, choose j. And then I raise it to powers of k minus j u. Done. So now we'll be able to take any Newton equation, Navier-Stokes equation, whatever, anything that has derivatives in it. And sometimes they have second order derivatives because there's acceleration or there's harmonic force. Sometimes they have fourth order derivatives because there's some thin sheet. And we know how to discretize it. Now, as I'll show in the next snippet, this non-center thing is a little bit unnatural. There's a better way to compute the derivatives that not only takes care of translational symmetry, because you can notice all these things are translational invariant, because if I add constant to everything, it cancels in the differences. That's fine. Derivatives of the field don't care about changing the value of all fields by constant. But also there are symmetries. For example, sometimes the laws of nature are invariant at time reversal. Instead of going forward, we go backwards. And they're written in terms of time derivatives. And these non-centered guys are not obviously time reversal invariant, so there is something to worry about.